Hello, everybody, and I'm happy to see you back to my channel. Gorgeous music is what we all enjoy in life, and that's why we love the tape machines. But those tape machines must be kept in very good condition in order to play the music the way it was intended to. We all know that those machines are fairly complicated devices. There are a lot of parts, a lot of electronic subassemblies, mechanical parts, and whatnot, and they all need to be kept in good condition for the tape recorder to produce really, really good sound. There are many different routines for optimizing the sound of your tape recorder, and today we're only going to touch on one of them. Yes, there is a whole slew of procedures for mechanical adjustments, for playback, equalization, recording side, and whatnot. There are several different steps you have to take in order to make sure your tape recorder sounds its best. Today we're going to talk a little bit about playback equalization adjustment. There is no big mystery about that particular calibration step, and many of you probably have done it. But some people are not really aware that there are different ways of doing this type of adjustment. And yes, the most common way involves going step by step from one frequency to the other, calibrating the trim pad or what you have in that particular machine, trying to achieve the flattest possible frequency response. So yes, this type of test tapes with multiple frequencies, each one may be taken 15 seconds, maybe a little bit more, and you may have choice of very few, as few as maybe 5 frequencies, and as many as maybe 12 or 15 in some cases. Having more frequencies makes it a little bit more flexible, but really is not necessary. You only need few well-selection frequencies. But be it as it may, that procedure with going from frequency to frequency is the most standard one. And we're not going to cover it today because everybody kind of knows how to do it. And if not, if there are any big questions about that, we can devote the whole video to that procedure, but it's not complicated. You need some test equipment, of course, but you do need test equipment for pretty much any adjustment relating to tape recorders. Like I said, tape recorders are complicated devices. So don't expect the shortcuts there. You will need some mechanical tools, you will need mechanical gauges, you will need a whole slew of different electronic pieces of gear. So you can cut some corners and you can do simplified procedures, that's okay. We're not going to get stuck on that today. But today I'm going to show you a couple more ways of looking at the frequency response, playback frequency response specifically. Those two ways are not commonly mentioned and discussed, so you might find them interesting. And I will show you the particular test tape that you might want to buy in order to accomplish those particular procedures. Most test tapes out there, to my knowledge, do not contain special signals for this type of calibration, which to me is a shame because they're not very complicated, and I would like to see more companies put those signals on their test tapes. And as I mentioned, to do it properly, you will need some test equipment. So let's look at our today's participants. The Studer A810 is going to be providing the tape drive for this test. It's got direct output, which will be connected to this particular head preamp. The particular choice of the head preamp is not critical, and you can take the standard output of the machine to perform this test. You don't really need the special head preamp for this type of calibration. And then you will need some meters and oscilloscopes. Don't let this particular setup scare you. You can do it with much simpler setup. This is simply what I have on hand, so I will be using this particular configuration. But like I said, you can do it with much simpler means. But first of all, you will need the proper test tape. And here we have the tape that I like using for this type of calibration. I have several tapes by this provider. They all come from the source in Germany. A particular gentleman there, he sells them on eBay. And they come in a variety of formats, speeds and whatnot. You just select the one you like. And the prices are reasonable. Now a little bit about the collection of tones and signals on this tape. It starts with a fairly conventional 0 dB 400 Hz tone for calibrating your full-scale output. We all know what it is, so I'm not going to spend much time on it. It only lasts for about 30 seconds. The next one is azimuthal adjustment tone. This is 16 kilohertz tone, and it's a long one. It's 60 seconds in duration, so it allows you plenty of time to calibrate your azimuth. Then you have something funny here, and we'll talk about in detail a little bit later. Then you have pretty much standard group of test signals, starting with 400 Hz at minus 10 dB reference level, and go from high frequency of 20 kilohertz down to 31.5 Hz. Again, this tape is for 38 centimeters per second or 15 inches per second. And the reference level is 320 nanowebers. That's probably what you're going to be using for your typical 15 inches per second to track tapes. At least it's one of those tapes that you could be using. Going on, this particular one is a frequency sweep. And you can use it with some test equipment to provide very nice smooth curve for your playback signal. I don't have that equipment set up, so we're just gonna ignore this particular one. But then we come to an interesting one. You see, it says multi-frequency signal, and that's exactly what it is. And this is a type of test signal that's gaining a little bit more popularity these days. Not enough popularity, I would say. I would like to see people using that type of signal more often. And in a few minutes, we'll see why is that. Pardon my light interruption, something wrong with my breaker or power line, so I sometimes lose portion of my workshop lights, but there should be still enough for us to see this video. So for now we're going to ignore those two first blocks, which are fairly trivial in their application. You don't need much tutoring on those. You can do it. You can find plenty of information online about how to use those tones. So let's go to this group. And here you will have interesting signal. You will have 400 Hertz for about 5 seconds, then switching to 18 kilohertz for about the same duration and going back and forth like that. And what's so good, you will ask? Okay, let's see. We're only going to be looking at the instruments you currently see on your screen. The oscilloscope, the two-trace oscilloscope. You may have just single trace, and that's going to be fine if you do one channel at a time, which actually is the way you should be doing it. When you are new to the procedure, try not to do too much in one step. Concentrate on doing one channel at a time well, and there is no rush. Just do it right. And you have 2 voltmeters reading the outputs. And we're going to be looking specifically at one channel. Let's make it left channel. But first, pay attention to both meters. As you can see, the frequency is hopping between 18 kilohertz and 400 hertz. Now watch the needles of those meters. You see it's making small shifts every time the frequency changes. And small shift means very small difference between response at 400 hertz and response at 18 kilohertz. And this is exactly what we would like to achieve. Let's play it again. You see the change here is on the order of half dB, and that's exactly how I usually set my channels. About the same on this channel as well. So that's, I would say, that's about perfect calibration. But again, we're talking about units that have been already calibrated. So we expect it to be pretty much spot on. But what happens if it's not calibrated yet? So let's see. I will intentionally detune my left channel, and just to make sure I can return to it, I will calibrate it down by 3 full turns of the trim pot. Okay, I turn my trim pot down 3 turns, and it is a multi-turn trim pot, so it should not be huge distance. But let's see what it does. Let's play the same area again. And watch the left meter. See how crazy the needle on the left meter is now. That's because I detuned the system. And now watch what happens when I start going back. You see those jumps are getting smaller. Let's play it again. You see, they're getting smaller. They're not perfect yet. I think we are basically in the area. There is almost no change on the left meter, simply because I've been adjusting the trim pot on that particular channel. So basically at this point, what happened? As we were hopping between two frequencies, I was adjusting the high frequency trim pot on my preamp. It happens to be this one, until I saw the needle to become almost stationary between two transitions, going to low frequency from high and from high to low. You can accomplish it, but it takes a little bit of dexterity and paying attention to the screen, because you have to do it while the screen shows high frequency, because that's what you're adjusting. Let's see it again. See those very small variations now, and watch the screen. Low frequency, high frequency, low frequency, high frequency, low, high, low, high. Almost no change. So I would say that's a pretty good calibration, and it was done in a matter of seconds. Okay, maybe a minute. When you know your procedure, you can do it very quickly. Don't pay attention to the fancy screen above it. We'll get to it in a minute. As we are rewinding tape toward this particular test on the test tape, we're going to make a quick stop at the frequency sweep. So let's see what it looks like on oscilloscope as the frequency sweeps from low frequency to high in one smooth swoop. It starts at very low frequency and it starts getting faster and faster. Frequency is getting higher, so you have to switch the sweep on your oscilloscope to keep pace with that particular signal. And if you have the proper recorder, strip chart recorder, you can plot very nicely that particular curve. Okay. At this point, we just looked at this particular signal. We're not going to do much about it. Like I said, we're going to be concentrating on the last signal on this tape, which is properly called the multi-frequency signal, because that's what it is. It's a signal that contains multiple frequencies, a whole bunch of them, played all at once. So now the machine is properly rewinded or rewound, should I say. And we can start this particular test and pay attention to the oscilloscope screen. It's going to have an interesting picture. And that's exactly why it is called multi-frequency signal. Because this is what it contains. It contains a whole bunch of peaks. This is a spectrum analyzer screen. Okay, a few words about it. How do you get the spectrum analysis screen? You can buy a fairly expensive tool called spectrum analyzer. It will do the job. But you can also buy fairly moderately priced oscilloscope. In this case, it is HP 54600A model. And you will need to buy mass module for this scope. And then it becomes spectrum analyzer. Or at least it keeps to being scope, but also now has capability of do some mathematical operations, including spectral analysis. And that's what it's doing now. It's taking in that multi-frequency signal and it displays it in the frequency domain. You can see on the screen, the middle point of the screen is right now 12 kilohertz. So let's see it once again. Okay, the whole bunch of frequencies. You see, this one is 18 kilohertz. I already know what it is. I checked. But it goes lower. And how much lower, you might ask? Okay, let's go lower. You see, right now the whole screen is the middle point 1.2 kilohertz. So you see some low frequencies. Let me restart tape. It only lasts for about 30 seconds, so you have to keep rewinding it. But you see the peaks, you pay attention to the magnitude of those peaks. You see, this cursor line was put there for a reason. You can adjust it. And you can see that pretty much all peaks are about the same amplitude right now. And that's exactly what you would like to have. Once again, rewind. So while watching the screen, you can do the same type of detuning and then tuning again that I've done with the previous test signal. And you will see those frequencies drop as you detune, but then you can go back again. I'm not going to do it right now. Just take my word that it is how it works. But the bottom line is, you kind of seen the whole frequency response. You see it from very low frequencies all the way to the top of your spectrum. Now the question is, why most companies don't do it? I don't know. I don't have a good answer to that. I've seen some reports that it's becoming a little bit more popular these days to introduce this multi-level, multi-frequency signal in the test tapes. So if you ask me, I would say by all means, if you're buying a test tape, consider the one with that signal. At the very minimum, it is entertaining. And you can see in real time what's happening to some particular frequency. Like this one is, for some reason, is not very stable. I don't know why yet. I just note this particular behavior and keep moving. So this is it for today's video. I'm not trying to promote particular brand of test tape or particular brand of test equipment or head preamps, whatnot. I'm just showing you what else you can do besides just tedious going from one frequency to another one, which I hope, but I think you sometimes just have to do. And that probably provides the most precise way of calibrating your machine. But these two other ways are informative, and they also can be entertaining. So for this reason, keep them in your mind when shopping for the next test tape. So that's all for today's video. I hope to see you next time. And until then, stay well and goodbye.